Good afternoon. Our speaker today is Stefano Anselmi from the University of Padova. He got his master and PhD at the physics department in Padova under the supervision of Mattarese and Pietroni. Then he moved many different places, including Cleveland, Paris, ENFN in Padova for postdocs, and since 2022 is a postdoc at the physics and astronomy department in Padova, and he's also a member of Euclid since 2017. And he's going to tell us something about using baryonic acoustic oscillations for distances, I guess. Please, the stage is yours.
Thank you. Thank you for the nice introduction, and thank you for this nice invitation. In particular, thank you, Fabio. So I was here 6 years ago when I gave a talk on a preliminary work that I started. Now is going to this interesting or this provocative question. But let me try to tell you what we're going to talk about. This works. Should I use this?
No.
Clicca sullo schermo e attiva la finestra.
Thanks. Okay. Okay, this is my list of my collaborators in the last 7-8 years that we have been working on the baryon acoustic oscillations, and in particular, we want to answer this question. So what do we want, or what can we obtain from baryon acoustic oscillations? Generally, in cosmology, the general agreement is that we can obtain late-time cosmology-dependent accuracy distance method. So I will try to, but what that really means and at what level this is true, I will try to answer this question, and I will discuss new proposals and implications. So what is the goals of the BIO distances? Is to constrain cosmological models, in particular LCDM, and also to play with consistency tests, for instance, what is very well known as cosmological tensions since many years now. So how we play this game? So we usually combine BIO distances with other cosmological observations. So in this way, we can reduce the genesis among parameters. And also we can use the BIO distances alone to do, for instance, what goes under the name of dark energy detection, or late time acceleration detection. So here are 2 examples of what I just said. So we can do probe combinations. So for instance, here in this plot, the Planck collaboration combine the CMB measurement with the baryon acoustic oscillation distance measurement. And as you see, this divergence between the energy densities omega m and the energy density of the curvature omega k is greatly reduced by the baryon acoustic oscillations measurement, or the BIO can be used alone. But here, for instance, this plot is used to detect the W, the question state parameter for dark energy. And as you see, the BIO are really a constraining probes. That's a very nice story, but let's take a step back. So, and just briefly recalling what baryon acoustic oscillations are. So the picture that we have in the standard cosmological model is that the initial fluctuation in gravitational potential, they shows up and they are measured as temperature fluctuations in the cosmic microwave background. So they are measured with very good precision by the Planck satellite, as we see here. So the same oscillations, they are detected in the clustering on the galaxy correlation function, where we see that around 100 megaparsec in the shade scale, there is this feature, this peak and this dip around these scales that are given by the baryon acoustic oscillation feature. But what is the physical picture that we have in mind? So in the primordial universe, when photons and baryons were tightly coupled for each initial over density, under the opposite effect of pressure and gravity, and acoustic waves were generated, and it propagated until the baryon photon decoupling time. And at that time, it got frozen. The acoustic wave got frozen in distribution of baryons. And because of the gravitational coupling with dark matter, then it got imprinted also in distribution of matter, of dark matter and baryons. So I mean, this length scale can be measured using the cosmic microwave background temperature measurement. And in the BAO, sorry, in the galaxy distributions, these are the BAO rings. Okay. So what is interesting is that the idea is that this length scale can be measured at early times, at late times. This is one of the idea that is behind the building of the ruler. So what is this scale? This scale is called the characterize scale. It's defined as the co-moving length that an acoustic wave have traveled until the baryon photodecoupling time. And it roughly corresponds to the peak position in the galaxy correlation function late time. And what is interesting is that RD is a geometrical quantity, so it's independent on the primordial fluctuation parameters. It's another ingredient that goes in the building of the standard rule, the idea at least. So what do we do in practice? So in practice, what we do, we usually want to work in co-moving coordinates. But with the measurement are done in angles and redshift. We measure angles and redshift. So to work in co-moving coordinate, we assume cosmological values for parameters, and because of this assumption, we work in fiducial co-moving coordinates. And the assumption gives us what goes under the name of Alco-Paczynski distortion. That means that a sphere in the right cosmology will look like an ellipsoid in the wrong cosmology. So this distortion can be precisely computed for the monopole correlation function. This is the equation. Is the distorted or data correlation function is related to the true correlation function through these alpha parameters. That is called isotropic shift parameter, and it's defined in terms of dV. That is just a combination of the angular diameter distance and the Hubble parameter. Okay, so then what we are after, we want to measure alpha, we want to measure dV, and the idea is that we want to do this in a way that is background model independent. But we need to be careful because that's the Alco-Paczynski equation. Here we have the data, here we have the theory, but here we have to impose a model, we have to use a model here, and so we should be careful not to introduce unwanted dependencies, and I will come back to this in a minute, but before, I want to show you how the community, the cosmological community, how much the community rely on the BAO distance measurement. Here are two sentences that are taken from these two papers. It is done by basically CMB blank people. When they say, okay, there is this degeneracy, that's what I showed before, the omega M, omega K degeneracy, and BAO break the degeneracy. And here is written, okay, perhaps we don't know. I mean, we cannot, this degeneracy is very complicated, and perhaps there is some difference if you different likelihood. So we don't really, not sure, but we don't really care a lot because because BAO distance measurement tell us that really omega K is 0 and omega K is 0.3. So it's we rely more on BAO than on CMB, or at least they are the same level of reliability. And so then we will want to investigate this statement. And so the first question is, how cosmology independent are these measurements? So in practice, if you check the cosmological literature, you will find that BAO distances are employed to constrain basically any cosmological model. So the implicit assumption behind this is that that BAO gives us cosmology independent accurate distance measurement. And this implies that the inference is done without cosmological model assumption. So the question that we want to answer today is, at what level is this true? So again, that's a slide that I showed before, but just to recap before explaining this. So that's the Alco-Paczynski equation. As I said, because we want to measure dV in a way that is background, cosmological background, so independent on the cosmological model of the background, we need to be careful here in the theoretical treatment because we don't want to introduce unwanted dependencies. And why this is kind of complicated? Because since 15 years, we know that already at the BAO scales, already at large scales, we have to deal with late-time nonlinearities that distort the BAO feature in a way that is redshift dependent, as we see here, this different redshift, and in a way that we cannot ignore. This the most famous, if you want, or linear effector, or the most relevant, linear gravity, phase space distortion, and galaxy or halo, galaxy bias or halo bias. This is a relevant effect that we cannot neglect. And okay, so what do we do? This is just an example. This is what I call the minimal linear model for the correlation function monopole. So in the last probably 30 years, many different groups have worked out different templates or different models to predict correlation function monopole given a single cosmological model. This is the simplest one that for the correlation function grasp the main phenomenology. And this, I show this because it's simple enough to show what is the how we should think in playing this game. So here is the linear, this is the nonlinear correlation function, monopole. Here is the linear power spectrum that we get from Boltzmann codes. And this depends on the energy densities, baryon, cold dark matter, and the scalar spectral units, XNS. A, this parameter is scale independent, but time dependent for LCDM, interface models, and pattern of Hall geometry. Sigma naught is damping of the view that we showed before, and depend on the growth, on the energy model, on the curvature, on the tracer. So if you want to estimate alpha in a way that is independent on the background and on the late time nonlinearities as well, you need to marginalize over the amplitude and also over the smoothing. Okay. I want to fit alpha, then the shape of the correlation function depend on energy densities and NS. And so we have to understand if we need to fit or marginalize over them and how. And so we spend quite a lot of time thinking about this problem. And so when we first started, we were able, because I mean, there's a lot of degeneracies here, so to have our Fisher matrix reliable, our Fisher matrix computation, we vary all these parameters that I showed you before. In this way, dV is properly estimated, but the problem is that the error is huge, it's around 100%. So after a while, we realized that if you take the sound horizon that depend only on the energy densities, and dV, the ratio of the two, they have similar error and a very high correlation coefficient. So the ratio of the two is very well constrained. And so then we can get to this final understanding. So then in this framework, we can obtain cosmological distances that are geometrical, so independent of the model coefficient parameters, that are Dark-energy model independent, we don't need to assume quintessence or LCDM, that are spatial curvature independent, and also tracer independent. And we name these purely geometric Baryon acoustic oscillations. It's not clear what happens if you have modified gravity models, or that, for instance, dark matter, dark-energy coupling, that depend on the coupling, depend on the logical, the modified gravity model, depend how close you are to the Planck constraint, etc. So, okay, after telling you this story, then I go back to what is going under the name of BA only distance measurement, that use a template fitting, for which this means that template fitting basically means nowadays that cosmological parameters are kept fixed. That's our Kubatsky equation. These are the data. And here is basically, I call this C fixed, the minimal model, very close to the minimal model I showed before, is alpha. And this broadband term is added. This was chosen with embodied simulations several years ago. And where it was chosen because gave the least biased result for alpha. And so then these parameters, energy densities, NS and sigma naught, the damping factor, are kept fixed. And these parameters are varied, and this is fitted, this is marginalized. And so this should take into account of residual systematics, should take into account of nonlinearity, residual nonlinearities, and also should propagate somehow the error and the errors and uncertainties that haven't been propagated because of this assumption. This is the idea, but nevertheless, because of this fixing, then the result is biased, is written here. And so there is a prescription to unbiased alpha, and this entails multiplying by RD fiducial over RD, where RD is the sound horizon. This is a number, this is the true sound horizon. So then we can ask, given this procedure, this descriptions, if the errors on alpha are properly estimated, for instance. And so there are two problems. The first is the parameter fixing I just discussed. The second is which correlation function model should we use? As I said before, there are many, and I will go back to this in a minute. There are many different correlation function models. Which one do we use? Do we get different result? So the two questions are relevant to get to do a proper inference. So problem one, parameter fixing. So since we understood how to propagate all the uncertainties, we compared the correlation function model fitting without fixing parameters with the standard BAO distances, and we found that the standard BAO underestimate by nearly a factor of 2, this is the fiducial matrix investigation, the error bus. But still there is the problem 2, which galaxy correlation function theoretical model should we use? And the problem 2 is the hardest one because the state of the art is to use numerical simulation to deal with the prediction of the 2-point correlation function. So we have ab initio simulations, meaning that the result of some, like the power spectrum, the correlation function of the spectrum, whatever you want to test, can be nearly convergent. So depending on the numerical resolution, for instance, of the simulation. Okay, we use dark matter halo identifiers, and they shouldn't really change our shouldn't be relevant for our goal, like find of friends, spherical densities, etc. In general, these are too slow to run MCMC for data analysis. There is a huge effort in this direction, like using machine learning techniques or using simplifying dark matter simulation. And that is for sure interesting direction of investigations. But what about galaxies? For galaxies, we don't have ab initio simulations, so we don't put initial condition and we let the simulation go without any extra information, because we lack a complete predictive theory for galaxy formation. So usually use like prescription like the halo population distribution to decide how many galaxies fit in a halo. So how do galaxies precisely calculate the matter field is still an open question. So for these reasons, since many years, for the BAO and also for other inference with the galaxy clustering, the correlation function model is used, a analytical one. But we should remember that it's not really known how to model in a way, analytical way, all these effects. There are different recipes in the literature, if you want, and they can be unbiased. There is no unique clear prediction. Like linear gravity, as I said before, there's been distortion, galaxy bias, how many parameters we should put on top of the cosmological one, and in which range of scales our correlation function model is working. So the reference to deal with this problem is to validate this correlation function model using body simulations and putting galaxies in halos. What is the meaning of validating? And we'll tell you now. So in general, the correlation function model starts from some fluid equation, and you can use different starting equation. We use different perturbation theory treatment. The most famous are the standard perturbation theory, effective theory, large-scale structure. Which perturbative order do we choose? Can we predict the range of scales where this is working? There are many different parameters. I mean, can we fix them? If we fix some of them, we can misestimate other parameters. How we choose the priors, that's a complicated game. Can we select parameters? Perhaps, but we should be careful because some of them can have a physical meaning. So that's it's a complicated game where the basic rule that is adopted is to take a correlation function model that is unbiased with respect to survey modes. That's a kind of a standard approach. But what about the error estimation? The error estimation, of course, as you know, is relevant because here is an example, parameter space when there's fake, now there are mock K LCDM data analyzed as flat LCDM, where AP and DT are just combination of the angular diameter distance and harbor rate. And there is this tension because we use the wrong model to analyze the data. And the tension can be driven by the wrong model, or and also we can get to a false detection because we have misestimated our error bus. So we should be careful. A mild tension can become strong tension and vice versa. Okay, so to attack problem 2 as well, we can rely on a very old idea, probably it dates back to Peebles. That is the following, that in linear theory, the observed correlation function is related to the matter correlation, the underlying matter correlation function, through a scale-independent factor. It is scale-independent for LCDM with essence and no need to assume flatness. So if we identify a preferred scale in the correlation function, this will be time and model independent. So we can measure dV in a model independent way. That's the idea. It was applied to the peak position until people found the peak position move is too unstable for decision cosmology. So by chance, I would say 7 years ago, well, 8 years ago, we found that there is a peak point, that is the midpoint within the peak and the dip, that is as interesting feature is geometrical, so is sensitive to NS and tau, is so independent of the Promoter fluctuation parameters. It's redshift independent at 0.5% level, so it's linear, so it's really sensitive to nonlinearities. And so we can exploit in 1 and 2, we can perform distance measurement in a way that is independent of the background. So how we got to this from a wrong plot, meaning that we were sitting down with this plot and we divided by the growth factor square, so dividing out the redshift, the linear redshift growth, and we saw that different redshift, all the correlation function, they went through the same point. So then we start asking what that means, and in particular, if you can exploit this feature for cosmology somehow. And so after a while, we got to the Anklo-Paczynski equation, and that can be rewritten in the following way. Now this is just this definition, but it's the same equation. And if you have a linear position, then here we can use the linear theory that we think we understand much better than linear predictions. So we can use Boltzmann code like the public count and class codes. And so then we can estimate the dV, actually SLP divided by dV, in a way that is independent of the model, on the 2-point relation function model, and on cosmological model in the framework of the purely geometric Baryon Acoustic Oscillations. On the left-hand side, we use like a model-independent parametric fit. One can use Gaussian processor, whatever. Use a polynomial because that was the simplest idea we got at the time. We don't need to fix parameters, and there is no fiducial cosmology dependence in this exercise. So we applied this to the SDSS galaxy sample, low Z and CMAS, and we estimate the cosmological distances, and we found for low Z this to be consistent with the standard BAO for the pre-reconstruction data here, and I will come back to construction later. We found conveniently that we got smaller errors. So then we go back to what I showed in the first slide. So BAO can be used to do what is called the Kenji detection. So basically here there will be a line that is not there here in this plot, where what is the idea? We take different BAO distance measurement, different redshift from different galaxy surveys, and then we put them together. We assume the Friedmann equation with omega k is a free parameter as well. And then we see how, at what level the detection, the delay time universal acceleration is detected. But as you see here, this is the posterior of the combined BAO. And we got two parameter values that are pretty, let's say, extreme or different from Planck, that is here, basically. And so we are basically relying on an extrapolation here because the embodied simulation that we have, they are all flat and they are very close to the Planck best fit. So, I mean, can we really trust this plot if we don't have tools to calibrate or to investigate our theoretical tools? So in general, the BAO distance should be flexible enough to be used for many purposes. For instance, the Kenji detections, inverse distance ladder, cosmological tensions, BAO consistency test, etc. It's also possible, in principle, to use only one BO distance. Why not? That's not forbidden. So then, if we can ask how wide the parameter range should be, that's a typical question, and the answer is will be the widest possible, given what we can try to achieve, of course. So, so the story that I told you is not the end of the story, because especially nowadays, more and more, all the BO distance measurement are given using BO reconstruction as well. What is BO reconstruction? So BO reconstruction rely on this idea that is an interesting idea. So because of late time nonlinearities, the information is not all in point correlation. There is also something in the higher correlations, like 3-point correlation function, 4-point correlation function. So if you are able to undo nonlinearities, so send back galaxies to the initial position, then we can recover all the information in the 2-point correlation. So this data treatment can amplify the signal to noise and reduce nonlinear effect. Is approximated. It's not clear that one can do this in a rigorous way, but I mean, we can. People are working in this direction and they get better and better result. But the question is, how are we assuming LCDM at what level? And also the algorithm, in the input of the algorithm, there are other cosmological parameters like the growth rate and the matter galaxy bias that is cosmologically is tightly connected to cosmological parameters. So then, in principle, one can vary all of this. This is not done, but I mean, it will be a huge effort. Perhaps it's possible, but for now, the official BO distance measurement are given with this treatment. So what are the caveats? So the standard BO caveat is that the BO fitting, for instance, fixed parameters to flat random CDM, close to plant best fit. The same applies to the BO reconstruction. So in general, is a problem for all the galaxy clustering, I would say, investigations. So the survey mocks and MADI simulations assume flat random CDM, and the cosmological, the simulations also, they assume parameter values that are close to flat random CDM plant best fit. So we need to model linear physics for a wide parameter range, something that we really want to do if we want to have this, to draw this plot, for instance. Yes. So what do we learn about cosmology? So the aim, in general, is to test cosmological models with galaxy clustering. So when we compare data versus theory, we are testing cosmological models assumptions. This will be easy if, given one cosmological model, we have a unique prediction for the galaxy correlation function. This is not the case, so we have to rely on correlation function model, where we add extra assumptions. So when we compare data versus theory, we are testing cosmological models and the galaxy clustering model assumption at the same time. So what we are learning about cosmology is a little bit more complicated, and we should think about this. So what is the linear point? Is a complementary approach that attempt to reduce non-cosmological assumption in this game, and is a more data-driven approach, if you want. So why? Again, just let me stress this again. Correlation function model, we have to use description to model linear effect, and we have to decide which end of scale this is working, and using MADI simulation is done fixing parameters. With survey mocks, we can obtain unbiased result, but what about the error estimation? Unbiased result, at least where we are survey mocks some parameter range. Are we doing parameter estimation or consistency checks? So here point, as I said, is a new observable, is the peak digit point. We exploit a model independent estimators, we can propagate errors. We are limited by the embodied systematics. We rely strongly on embodied simulations. And here there's a problem in general for everyone, because we have ab initio simulation for dark matter, but what about galaxies? So this is to conclude. So the cosmological applicability of the standard BO distances is clear. So after some work, we came out with this purely geometric Baryon Acoustic Oscillations that give us cosmological distance measurements that are independent of some cosmological background models. You don't have to fix parameters to flat round CDM. In practice, we can do can perform this period geometric baryon acoustic oscillation measurement using the correlation function model fitting propagating the uncertainties. And with this, we found with the Fisher matrix investigation that the errors are underestimated by nearly a factor of 2. So, but which model do we use? How many parameters, millions of scales we use our theory, our model? The other point on the ruler is a complementary approach that is more model independent in the sense that we don't have to assume a correlation function model to play the game. There is a lot to do. So what happens if we open the parameter space in a wide parameter range? Can we add the quadruple to point correlation function that gives us extra information? Can we combine with other observations? We should combine with other observations. What happens for different galaxy populations, observational systematics, what are the light cone effect, etc. And thank you.
Questions for the speaker? Okay, yeah, go ahead.
So you have a curiosity and a question. So the curiosity is, so can you use one loop to do perturbation theory to model this linear point, and what is the reliability of this?
It's not really the idea, I mean, because the one loop, two loop, three loop, or effectively whatever you want is like they are. This goes under this. I mean, we use the David approximation as a tool to cross-check the embodied simulation result, but like when I was showing this, yeah. So like when people talk about one loop, three loop exciter, they usually talk about effectivity of large-scale structure, or they talk about SPT, and that's a way to model usually linear gravity. It's a little bit more complicated for also galaxy bias. RSD is a little bit more complicated, but that's yeah. So it, yeah. I mean, it's,
and how,
so the idea is not to use this actually. So.
okay. And how this model can be used, for example, for the Euclid spectroscopic sample to constrain.
I mean, I'm in Euclid, so I'm leading the linear point project, and I will tell you. I mean, we are using the flagship to investigate. I mean, the flagship simulation. We are studying how these linear points behave given the redshift, given the halos, and for now everything seems to be okay, but we are not done.
I have a curiosity refer to this idea of sending galaxies back.
The Baryon
reconstruction.
yeah.
How does it work in rough terms?
Yeah, that's not something that we do, because that's you have to add extra assumptions. So basically, they use the dog. I mean, there are many different ways. So basically, if you want, the basic idea is that you run a simulation back. So instead of starting from linear, you start from linear initial condition, then you go to non-linear, and you can invert in principle, but then you get complication because you have shell crossing, so it's not really doable. So there are approximations if you want to obtain this. And so then also we don't have
the Dovich approximation to an evolved simulation to send.
Yeah, that's the basic old idea of 2007. Then people did something better, so there is some. Yeah, there are many approaches, there are many papers that.
And the idea is that this would be applicable to real data.
This was applied. This is applied to real. This is a standard. So that usually, like also I think also Euclid, they will provide, for sure Euclid also, 2-point correlation functions that are what we call post-reconstruction, where this is adopted, or pre-reconstruction, where this technique is not adopted. And but I mean, it's tricky because I mean, of course, we don't have simulation out there. We have galaxies, so then to send back galaxies, you have to add assumptions. You have to know the bias, and how you know the bias. The bias you really know because you know cosmology. So I mean, it's a bit of.
Okay, and then yeah, Fabio.
Your recommendation on the use of pre-reconstruction?
I recommend pre-reconstruction. No, because we have less. I mean, basically, I mean, okay. So here is I would say work in progress, and people can. For now, I haven't seen how anyone varying these parameters. So if you don't vary this parameter, you have 2 extra assumptions. And then also it's not clear, I mean, if you move away from LCDM, it's not clear how the total approximation or how you play this game. So that's for sure, in general, naively, you have less assumption. So that's my, but I think, I mean, so Carlo perhaps know better than me. I think in Euclid, the official PAO pipeline will not give PAO distances without reconstruction. That's what I saw in the key project papers. So, but there will be like the 2-point correlation function will be released for sure.
But like, for example, can you implement this method in Clore, for example?
The reconstruction.
Yeah. I mean, your method.
But yeah, yes.
In the official cosmological.
Yeah. I don't see why not this. This will be implemented, I think. Like Elena is basically she's working this. And she has a very good, I mean, she has a very good technique that is much better than Zadovic's one. Then, I mean, actually doing this game, it's very difficult to control assumption. I discussed also with Elena that it's not trivial.
Okay, no questions from online, no other questions here, so thanks again.